Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Broadcast storms, infinite traffic loops, and network-widely congestion, these are just a few of the potential consequences of unregulated switching environments. In episode 113, titled Spanning Tree Protocol: Loop Prevention for Switches, we focus on the key protocol that protects Layer 2 networks from destructive loop conditions. Unlike routers, switches do not use a time-to-leave field in Ethernet frames. That means once a frame enters a loop, it can circle indefinitely, consuming bandwidth and creating broadcast storms. Understanding how to prevent these conditions is vital, both for real-world roles and for success on the certification exam. Spanning Tree Protocol, or STP, is the primary mechanism used to ensure a loop-free topology at Layer 2. When switches are interconnected with redundant links, STP identifies a single active path between any 2 points and blocks all others. These blocked paths are kept in reserve and reactivated only if the active path fails. This balance between redundancy and loop prevention is what makes STP so critical. The protocol also adapts dynamically to topology changes, ensuring that block paths can become active as needed. An exam often includes configuration scenarios that depend on knowing how STP operates and responds. Layer 2 loops happen because switches flood unknown unicast frames and all broadcast frames across every active port. If the network has redundant paths without any loop prevention protocol, those frames can circulate endlessly. Each switch keeps repeating the frame, multiplying the traffic across all redundant links. The result is network instability, severe congestion, and even device outages. These loops can happen instantly and are difficult to diagnose without tools like STP in place. The certification exam will often ask you to recognize the causes and effects of these loops and the mechanisms that can stop them. To prevent these conditions, Spanning Tree Protocol initiates a loop avoidance process. It begins by electing a central device known as the root bridge. Once elected, each switch calculates the shortest path to this root bridge and designates ports based on that calculation. All redundant paths that are not part of the shortest path tree are placed into a blocking state. This creates a logical loop-free network even though physical loops still exist. The active topology always has one best path per destination, and backup paths remain idle until needed. Understanding this process is fundamental for exam readiness. The election of the root bridge is based on a value called the bridge ID, which includes the bridge priority and the switch's MAC address. The switch with the lowest bridge ID becomes the root bridge. If all switches have the same default priority, the tiebreaker is the lowest MAC address. This automatic election process can be influenced by administrators who manually assign bridge priorities to control which switch becomes the root. Knowing how to interpret this election and which switch will win is a common question format on the exam, especially when reviewing network diagrams. Once the root bridge is chosen, all other switches assign port roles. The port that leads toward the root bridge is called the root port. It is the switch's single best path to reach the root. For each collision domain or network segment, the port that offers the shortest path to the root is designated as the designated port. All other ports are placed in a blocking state to prevent loops. The result is a tree-like structure with no loops and clearly defined paths. These port roles, root designated and blocked, are critical to understand and are featured prominently on exam diagrams. Each port also has a state that defines its behavior during STP operation. These states include blocking, listening, learning, and forwarding. A port in the blocking state does not send or receive data but listens for protocol messages. The listening state prepares the port by waiting for topology changes to settle. The learning state allows the port to gather MAC address information, but still blocks actual traffic. Only in the forwarding state does the port begin transmitting and receiving frames. These state transitions prevent loops during network changes, which are exactly the types of detail the exam may test. When a topology change occurs, such as a failed link or added switch, STP begins a process called convergence. During this time, port roles and states are recalculated and blocked paths may become active. While convergence is happening, there may be a temporary disruption to network traffic, especially if multiple changes occur simultaneously. The convergence process is essential to restoring a loop-free state and is designed to work automatically. Exam questions often focus on how long this takes, what behaviors occur during convergence, and how certain states are triggered. Rapid Spanning Tree Protocol, or RSTP, was introduced to address the speed limitations of traditional STP. Defined in IEEE Standard 802.1W, RSTP accelerates convergence by simplifying port roles and reducing the number of states. It merges the listening and learning states and allows for immediate transitions to forwarding under certain conditions. These enhancements reduce downtime during network changes and have made RSTP the default mode in most modern switches. The exam will test your ability to differentiate RSTP from standard STP in both behavior and configuration output. The differences between STP and RSTP go beyond convergence speed. While STP requires lengthy timers to move through port states, RSTP uses rapid transitions and proposals to reach forwarding mode faster. RSTP is also backward compatible, meaning it can coexist with switches running traditional STP if needed. However, full benefits are only realized when all switches in the topology use RSTP. Most current switch platforms default to RSTP or offer it as a simple configuration option. Recognizing these differences is essential for answering exam questions about performance and protocol compatibility. Redundant topologies are designed to increase network resilience by providing multiple paths between switches. Spanning Tree Protocol supports these designs by selecting one active path and keeping others in standby. If the active path fails, STP reconverges and activates a backup. This creates a self-healing network that balances performance and stability. The certification exam frequently includes scenarios where you must evaluate redundant links and determine which ones are forwarding or blocking based on the root bridge and path cost calculations. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Spanning Tree Protocol uses several timers and intervals to manage port transitions and maintain stable topology changes. The most common timers include the hello timer, forward delay, and max age. The hello timer controls how often the root bridge sends out bridge protocol data units, or BPS. The forward delay timer dictates how long a port stays in the listening and learning states before transitioning to forwarding. The max age timer determines how long a switch retains BPDS from the root before considering the path lost. These timers work together to ensure smooth convergence and to prevent loops during state transitions. On the exam, understanding what each timer does and how it affects port behavior is important when interpreting convergence scenarios. Network diagrams are frequently used to visualize how STP operates. These diagrams typically show a series of switches, links, and port labels indicating roles, such as root, designated, or blocked. To identify the root bridge in a diagram, look for the switch with the lowest bridge ID or one explicitly labeled as the root. Blocked links are often indicated by slashes or annotations, while forwarding ports are shown with solid lines. Being able to interpret these diagrams is a key skill for the certification exam, as you may be asked to determine which links are active, which ports are blocking, and how changes would impact the network topology. Troubleshooting STP issues involves identifying symptoms like unexpected link blocking, slow convergence, or even undetected loops. For example, if a port that should be forwarding is instead blocking, it may be due to incorrect path cost calculations or misidentified root bridges. Slow convergence can be caused by high forward delay values or incompatible protocol versions between switches. Loops might still occur if STP is disabled on a segment or if configuration errors prevent proper blocking. The exam may present symptoms and ask you to diagnose the root cause based on port roles and protocol behavior. Misconfigurations in STP can introduce instability into the network. One common issue is manually setting bridge priorities in an inconsistent or conflicting way, which may result in unintended switches becoming the root bridge. Another issue involves inconsistent VAN assignments on trunk ports, which can confuse per VAN spanning tree calculations. If multiple switches think they are the root bridge for the same VAN loops, and traffic disruption can occur. Being able to recognize these misconfigurations in command output or network diagrams is essential for accurate troubleshooting on the exam. The STP interacts with VLANs through protocol variants like per VLAN spanning tree, or PVST, and rapid per VLAN spanning tree, or RPVST. These protocols create a separate spanning tree instance for each VLAN, allowing for customized root bridge placement and path selection across segments. While this increases flexibility, it also adds complexity. Each VLAN must be considered independently, and inconsistent configurations between them can lead to performance issues. On the exam, you may encounter questions that require analyzing per VLAN behavior and identifying which instance of STP is in use. Disabling spanning tree protocol is highly discouraged in most production environments because it opens the network to immediate loop conditions. However, in rare cases, such as tightly controlled lab environments or point-to-point connections, administrators may choose to disable it. Doing so requires careful design, strict cable management, and alternative loop prevention measures. The risk is that even a single configuration mistake or cable error can bring down the entire Layer 2 domain. The exam may ask when it is appropriate to disable STP and what precautions must be taken to avoid disaster. Spanning tree protocol appears in many exam scenarios, especially those focused on switch behavior, port roles, and network resiliency. You may be asked to identify port states such as blocking or forwarding based on topology diagrams. Other questions may require recognizing how loops occur in networks where STP is missing or misconfigured. It's also common to see simulations where you must adjust bridge priorities, observe convergence, or troubleshoot why a switch is not forwarding traffic correctly. These questions test both conceptual understanding and practical application of the protocol. In summary, spanning tree protocol is the cornerstone of loop prevention in switched networks. By identifying a root bridge, assigning port roles, and blocking redundant paths, STP ensures that Ethernet frames do not circulate endlessly. It supports network resiliency by allowing for redundant links that activate during failure events. Protocol variations like RSTP and per VLAN modes provide additional speed and flexibility. For anyone preparing for the certification exam, mastering this topic means gaining control over one of the most powerful and essential mechanisms in enterprise networking. To conclude episode 113, remember that spanning tree protocol serves as the primary defense against switching loops at Layer 2. It elects a root bridge, determines port roles and states, and dynamically adapts to topology changes. Rapid spanning tree improves on the original protocol by reducing convergence time and simplifying transitions. These concepts are critical for maintaining stable, scalable, and resilient networks. For the exam, a strong grasp of how STP and RSTP function will help you analyze scenarios, identify misconfigurations, and ensure loop-free forwarding across the switch infrastructure. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.